So this is going to be the first of the asynchronous videos that I'm going to be posting. So my goal in this course is I'm going to be posting a lot of the lectures asynchronously for you to watch anytime. And then we'll also talk about lots of the material together in class. But it's a 5-hour class. We meet only 3 hours during the week. And so I'm going to have some extra videos that I'm going to be adding in. So a lot of the theory and a lot of the lectures will be online. And then that means that we'll be doing a lot of problem solving together and reinforcing a lot of the material that we've talked about. So that's my goal with these videos. So the first of these videos, we're going to start with section 6.1. So section 6.1 is all about inverse functions. And so I want to talk about what that means, which functions have inverses, which do not. And then there's a few nuances that we need to talk about. So an inverse function, two functions are inverses. So f and g are inverses if f composed with g, this is inverses with respect to composition. So whenever anyone talks about an inverse function, they mean in this sense. So if f composed with g and if g composed with f are both just x. And remember f composed with g, so just recall that f composed with g, for example, means f of g of x. Okay, so that's just the notation of what a composition of functions means. That's probably familiar, but just in case. So for example, if you were to take the function f, which is say x cubed plus 2, and the function g, which is say the cube root of x minus 2, it turns out that these functions are inverses, because if you were to take f of g of x, remember what that means is you're going to take g, and then that's going to be what you plug in for x in f. So this is going to be g cubed plus 2. And that works out when you cube a cube root, you get the radicand, the thing under the radical, x minus 2 plus 2. And that's x. And likewise, when you compute g composed with f of x, what you're going to get is you're going to end up with the cube root of x cubed plus 2 minus 2, right? So you're going to take f and plug that into x for g. So you end up with a cube root of f minus 2, f of x being x cubed plus 2. And this works out to be the cube root of x cubed, which is also just x. Okay, and so these two functions are inverses. Once you've established that two functions are inverses, or whenever we're talking about inverse functions, what we can do is we can write, instead of writing g of x, what we'll do is we'll write f inverse. And this notation is just a notation. It doesn't mean anything more. But this -1 comes about, it's kind of borrowed language from inverses that you're already more familiar with. So for example, 4 and 1/4 are inverses in the sense of multiplication, not in the sense of composition, but in the sense of multiplication, because when you multiply them, you get the identity. And in this case, when you compose these two functions, you get the identity. You get the function that just spits out x. It doesn't do anything to it. So that's the identity function. So this -1 notation you're familiar with from algebra courses. That -1 notation is just borrowed from the multiplicative inverse notation. So whenever you see f inverse, all it means is the inverse function. We're not talking about fractions necessarily. It's just notation that's borrowed from inverses that you're already familiar with. So there we go. So that's the notation for inverses. Okay, we just write f to the -1. And again, that's just notation for the inverse function. Not all functions have inverses. Okay, so another example that we need to talk about is if I were to take x squared plus 2 instead of x cubed plus 2, and say g of x is the square root of x minus 2. It turns out that f composed with g of x is just x, and that's no problem. So what happens is you take the square root of x minus 2, you square it, and then you add 2. And it turns out that this is going to be, so the square root of x minus 2 squared is x minus 2 plus 2, and that's going to be x. There's a subtlety here, though, in that it looks like if you take the function f of x equals x, that's true for any value of x. But if you look at this expression, the square root of x minus 2, that's only going to be a well-defined real number when x is at least 2. So for example, you cannot plug 0 in to the left side of this equation, but you can plug it into the right. So this equality is probably a little bit misleading in the sense that they're not always equal, but when they're both defined, they're always equal. It's just that this expression over here is only valid when x is at least 2, whereas this expression is valid for any x. So there's a little bit of subtlety here, and that subtlety is going to matter because if you were to look at g composed with f, for example, this becomes even less subtle, but you can already see that there's a problem here. If you take g composed with f, we're going to take the square root of x squared plus 2 minus 2, and that's going to be the square root of x squared because the 2's will cancel. And that's not going to be x. That's only going to be the absolute value of x, which is a piecewise function. It's defined as x when x is greater than or equal to 0, and negative x otherwise. So in particular, if you were to look at g composed with f of x, this is not even going to be equal to x when x is negative. Okay, it's going to be equal to negative x. So you do not have inverses here. And there's a geometric story about what's happening as well. So let's look at x cubed plus 2 and its inverse. So if we were to go back and look at the function x cubed plus 2 and its inverse function, I'm going to use the new notation now, the cube root of x minus 2. And if you were to graph them, well, x cubed plus 2 is just going to be the function that's going to look like x cubed. It's shifted up 2 units. Everything's fine. And x cubed, the cube root of x minus 2 rather, is going to look something like this. Okay, so it's going to look like the cube root of x, and then just shifted 2 units to the right. Okay, that's what that minus 2 on the inside does there. And so if you think about what this means, if you think about how these two relate to each other, you can imagine kind of picking up, this is almost easier to do in person, but if you were to pick up the one graph that you have, and then you were to rotate it that way. So you kind of flip it over the line y equals x. So I'm going to add in a line here, y equals x. And so if you were to rotate it about that line, excuse me, reflect it about that line, what you would end up with, okay, would be the inverse function. Okay, and so it's just reflected about this line y equals x. Okay, and so inverses, it turns out, are going to have very similar graphs. It's just that they're going to be reflected about the line y equals x. So that's how they're going to differ from one another. Okay, and so that's the story. That's how you can geometrically find an inverse function. That also explains why x squared plus 2 does not have an inverse function. If you were to do this process with the function x squared plus 2, if you were to do this process, what you would end up with, I'm not going to call it the inverse because it's not, but if you were to take the square root of x minus 2, you do not get the same graph, because if you take x squared plus 2, that's just a plain old parabola shifted up 2 units. And if you were to rotate that about the line y equals x, what you would get would be something like this parabola. Okay, but the problem is that this parabola on the right is not a function anymore. And in fact, when you talk about square roots, we're only talking about non-negative outputs. So you have to get rid of the bottom value here. And in fact, if you were to what's called restrict the domain, if you were to change the domain, instead of saying, I want to consider all real numbers as inputs for this function f, if you were to change that and say, I'm going to consider all the non-negative real numbers as inputs for the function f, then you actually do have a function that has an inverse and everything's fine. And so that process is called restricting the domain. And we'll have to do that a few times when we talk about some functions later on in the course. So particularly the trigonometric functions, sine, cosine, etc. But you can see right away that because this function x squared plus 2 fails the horizontal line test, that would mean that when you flip it, so when you flip it and draw the parabola fails the vertical line test and therefore is not a function. And so if you want to know whether or not a function has an inverse, all you really need to know is, does it pass the horizontal line test? Because then when you flip the function, when you reflect it about the line y equals x, the resulting picture that you get would be the graph of a function, because it would pass the vertical line test. Okay, so in a nutshell, that's the horizontal line test. It turns out that a function has an inverse if and only if it passes the horizontal line test. And again, just to be explicit about what that means that take any horizontal line you want. If the graph of the function intersects any horizontal line at most one point, then it passes the horizontal line test. In this case, the horizontal line test has failed because there's 2 points here and here. For example, there's at least one horizontal line where the function intersects at more than 1 point. Okay, and so that's a problem. So that's, again, a visual example of why the x cubed plus 2 has an inverse, but x squared plus 2 does not. So we've already gotten into some of the subtleties here, but I think at this point I should introduce this idea of a function. So we say that f is 1-to-1. This is going to be formally how we say whether or not a function has an inverse. But f is 1-to-1 if f has the following characteristics. So if f of a equals f of b implies a equals b. Okay, that's a way that you can actually codify the horizontal line test, because what this means is that if you have two outputs that are equal, the only way that that could happen is if you have the same input. And so, for example, if you take the function x cubed plus 2, it turns out that this function is 1-to-1. So this function is 1-to-1 because if you were to take f of a, that's a cubed plus 2, f of b is b cubed plus 2, and then set them equal to each other. What happens, so if f of a equals f of b, that implies that a cubed plus 2 is equal to b cubed plus 2, and that implies that a cubed is equal to b cubed, and that implies that a equals b. The reason why I'm allowed to take, I'm being slightly, I should be slightly more careful here. This implies that if I wanted to solve this equation algebraically, I'd need to get both sides. I need to get all the terms on one side and one side equal to 0. And then you'd have to factor this. This is a difference of cubes. And you'd end up with a minus b. And then you'd end up with a squared plus ab plus b squared. Okay, equals 0. And it turns out that this equation, a squared plus ab plus b squared, has no solutions. And you can check that just using the quadratic formula. So pretend that the x's, pretend that the a's are x's, and then try and solve it using the quadratic equation. And you'll see that there's no solutions there. And it turns out that the only solution that you really get is that a equals b. Okay, I'm being picky here for a reason. We need to be very careful when we're talking about what it means for a function to be 1-to-1 and when it has an inverse and so on. So there we go. So this function is 1-to-1. The function, on the other hand, x squared plus 2 is not 1-to-1. Okay, so this is not 1-to-1. And so there's a few ways that you can do it. You can try and get to a point where you can try to set these f of a and f of b equal, see if you get a equals b. It turns out you will not, because it turns out what happens in this case is that you would end up with a squared equals b squared, and then a would be plus or minus b, not just b. But a better way to do this would be, let's see if we can find an actual example that's a counter example to this. Let's see if we can think of a number, two numbers where they have the same input, where they have the same output, but different inputs. And for example, f of 1 and f of -1 are equal. They're both equal to 3. But of course, 1 and -1 are not equal. So here, this is one way that you could say that the function f is not 1-to-1, is that you have two different inputs that give you the same output. Okay, and so that's the story there. So f of 1 and f of -1 are equal, but their inputs are not. So that function's not 1-to-1. And of course, let me just tie everything up that I said very nicely. It turns out that a function f has an inverse. So function f has an inverse if and only if f is 1-to-1. Okay, and so this being 1-to-1 means that it passes the horizontal line test. Okay, and so that's really all the big pieces of inverse functions In the next video, we'll do a few more examples, and there's some surprising calculus that'll be helpful for us as well.